All right. We are on the precipice of the founding of cognitive psychology with the field of cognitivism. Okay, this doesn't say cognitive psychology, does it? So we're not quite there, but we're about to make this leap into cognitive psychology. So, cognitivism says that to understand behavior, we must understand cognition. So, this is going to be the bridge between the behavioristic approach, where we should only talk about the stimuli and the responses, and sometimes the stimulus is a reinforcement, and that will allow us to control behavior and so on. In cognitivism, they start to say, you know what, we can't truly understand behavior until we understand what's going on inside that black box. And one of the sort of prompts for why researchers started to say that is some nice classic research on rats learning how to get through a maze. It's a nice, simple, classic 1950s era research problem. So they placed rats into the maze, and in the top line where it says no reinforcement, the rats were placed in the maze and there was no food at the end. There was nothing to guide them towards the proper solution of the maze. They just, wandered around in there until they accidentally found their way out or whatever, had their own motivation for why they got out. So the top line is they never got any reinforcement. The little dot line is that says continuous reinforcement are the rats who there was always food at the end of the maze. And so every time they were placed in the maze, they had food as a guide and they would work their way through the maze. And what you see is the continuous reinforcement rats on day 17 are making their way through the maze with far fewer errors than the no reinforcement rats. So even though the maze is the same every single day that these rats are running through it, the no reinforcement rats still make a lot of errors while working their way through the maze, even on day 17, whereas continuous reinforcement rats are making their way through with very few errors. All right, now let's look at that dashed line. In the dashed line, the rats were not reinforced until day 11. So they spent the first, 10 days of their experience in the maze just wandering around and just coming out at the end of the maze and no reinforcement, they just got out. On day 11, they started having food at the end of the maze. Look at the rapid reduction in number of errors that happened in those rats. So they went from aimlessly wandering around and making a lot of errors to way fewer errors than the continuous reinforcement rats had been making. In just one day, they went from, oh my gosh, there's food in here. And then the next day they were like, I know where the food is, and bolted for the food. And they got even better in the remaining days, whereas the continuous reinforcement rats looked like they were kind of plateauing off, like they weren't going to get any better between day 17 and day 22. We don't have the data on that because the research wasn't supposed to be about that. Um, so, what this study turned out to display is that rats were forming mental maps of the maze, even in the absence of any kind of reinforcement for doing so. They didn't reveal that they had a mental map until they had the motivation to reveal it, right? Until the food was placed at the end. And then they rapidly displayed, I knew how to get out of here. I just was walking around to see if there was something that I was overlooking. But, well, there's food in the end. I'm going to bolt for the food at the end. They had developed a mental map, and they didn't get reinforced for the development of that mental map. They just developed it. They figured out the design of that maze, even though there was no reason for them to figure out the design of the maze. There was nothing to be gotten from it. So something's going on inside these rats' heads. You can tell I'm a cognitive psychologist because I already kind of blew it on that, didn't I? I said they were thinking, oh, hey, now there's food. Hey, I know how to get there. They were thinking thoughts, is what I'm assuming. The rats were thinking something. And that's what the researchers who did this study concluded too. They have to be thinking something. There has to be something more than their behaviors are the result of reinforcement. There has to be something else because they weren't being reinforced to figure out the structure of the maze, but they were able to reveal they know the structure of this maze as soon as there was a reinforcement. So mental maps. Another thing that illustrated, and this was almost at the same time in another lab, Another thing that illustrated that we've got to start considering the cognition of the learner was this research on latent learning. So this one's a little bit more complicated of a maze, but what we have is a starting place at the bottom, and then we have the reward at the end, which is the food box, right? And then you see these three paths. You could have path one, which is the straightest way. You just leave the starting place and run to the food box. Yay! Path two, you have to hang a left-hand turn, zig and zag, back onto path one, and then go into the food box. Path three, you start up, turn right, have to go around, go back up there, turn right again, and then you're at the food box. Okay. So as you can see, there are different places where we can block the rat's path. So if a block is put at point A, the rat can either go left onto path two and continue up path one, or they can go around path three and miss block A, that route. If it's blocked at block B, the only way around it is to take path three, right? So, oops, I wanted to double check that I hadn't illustrated like on the last one. Okay, so when they block path A, the rats knew to take path two, that was the fastest route and to get around that way. When the block was farther along, the rats knew to take path three. So even though they had been running up path one, they were figuring out the structure of this cage, or this maze, I should say. They were learning it. Again, latent learning is learning that occurs when there's no motivation, like no overt reason why you should be learning this. I didn't give you a reward for it. I didn't ask you to learn it. I'm not paying you in any way or something. You're just picking it up anyway. It's called latent learning. And the key thing with latent learning is that it doesn't reveal itself until the circumstances demand it. You may not even know it until the circumstances demand that you reveal it. And then you're like, oh my gosh, I do know this. So this study of rats and seeing that they knew which of those two paths, path two or path three, was most appropriate, whether the block was at block A or the block was at block B, they the researchers saw this and they're like, okay, those rats are thinking something. I am sorry, but something is going on inside these rats' heads. And so now we have two different labs making the argument that we have got to start thinking about the cognition that's going on inside the learner's head. Whether it's a rat or it's a human, we need to start considering cognition as a possible explanation for behavior. So cognitivism is a term that's actually used to describe the act of knowing and acquiring knowledge. So the act of knowing and the act of acquiring knowledge would be what we mean by cognitivism. So knowledge, see that at the base, this is something that I mentioned way back that, the philosophy, the epistemology, the how do we know things? That's at the heart of cognitivism. And this field acknowledges that we have got to think about these internal thought processes. We can't be like Skinner anymore, who, by the way, he was alive and doing research until 1990. So he was a diehard radical behaviorism until he died. But the newer people who are coming along were like, we can't do that anymore, Skinner, where we say it doesn't, that trying to describe the internal thought processes is just a trap, or that it's going to lead us down the wrong path, or those kinds of things. I think we're being led down the wrong path already by not considering these internal thought processes. So cognitivism, Tolman was probably the first in the 1930s to start raising this. He got attacked pretty hard, though. I mean, honestly, other people were afraid to pile on with this idea because the behaviorists were a lot more boisterous, charismatic. That's the word I'm looking for. They were a lot more charismatic. They got followers, and they're lot. I have to say, as a person who's been to grad school, being able to like wear a white lab coat and be in something that seems very much like a laboratory is kind of cool. And so I can really see how behaviorism was very attractive. It made it feel like you were doing something super concrete and super scientific. As opposed to like cognitive psychology, there's a little risk involved in the possibility that there's some kind of confound because you're trying to infer what's going on inside the person's head. So I can see it's risky. It's sort of almost sticking your neck out a little bit more when you say, this is my interpretation of what was going on inside my learners' heads, than if you're saying, I did the stimulus and this is the response that came out. Right? If you say, this is what I think is going on inside my learner's head, you're kind of taking a risk, and people can attack your logic or your conclusion or your interpretation. Whereas if you say, I gave the stimulus and this is the response that occurred, it's not about you, right? So it feels, I think, a little bit more risky. And so it wasn't really until like the mid 50s that people started saying maybe that thing that Tolman talked about in the 30s might be useful right now to explain these mental maps and this latent learning that lab after lab was seeing. Oh, that sort of looked a little strange. Oh, nope, that was, oh, I detected a signal and it was, I guess it was all right. Signal detection. All right, so now this actually, again, is very tightly connected with behaviorism. So in the 30s and in the 40s, psychologists, they were largely known as Gestalt psychologists at the time, were doing research on perception and sensation. And one of the things that they were trying to figure out is the thresholds for different kinds of stimuli. So, like, how loud does a sound have to be before you can hear it? How hard does a touch need to be before you can feel it? Right? How bright does a light need to be, and so on. And so they use this process called signal detection to help their participants describe whether they were experiencing the stimulus or not. If you've ever had your hearing tested, which I hope everyone has, you've had headphones on and they played little tones and you were supposed to raise a finger or your hand or something to indicate that you heard the tone. And you've had that experience where you're like, did I hear it? Or was that just me imagining I heard it? And so your finger's like sort of going up. That's signal detection. We're trying to figure out with these hearing tests the amplitude, how loud the sound needs to be in order for you to hear it at that frequency, right? So you've had experiences as a participant in a signal detection study. You just didn't necessarily know the words for it, right? One of the things that researchers found in these 1930s and 40s studies using signal detection is that the motivation level of the learner or the participant can affect whether the subject actually responds to the stimulus. So going back to your hearing test, you were really motivated to show that you could hear. And so you might have put your finger up times when there wasn't actually a stimulus. You were giving what we call false positives, where you said, oh yeah, I heard it, and really wasn't there. What you were trying to avoid, though, is you were trying to avoid misses where it really was there and you didn't hear it. So, as the person in that study, you were probably more willing to make a false positive than a miss, right? Like, you don't want them to think that your hearing's bad. You'd rather have them think that you're just overeager. But see, your motivation level can affect whether you're responding to the stimulus or not, right? So if you're trying to really hard show that you can hear properly, you might respond differently than if you didn't care as much what they thought about your hearing levels. And so they found that with all sorts of different kinds of learners, from rats all the way up to humans, right? Where they're like the rat's motivation level can affect whether or not they're detecting a stimulus. Fechner, back in 1851, is the one who first gave terms for the parts of the signal detection theory. So on the top there, we see you have either signal, and it could be a light, or it could be a tone, it could be, a touch, whatever. So signals on that left column, noise, he called it, which is not signal. Because, it's never signal free in the world, right? Like, even when nobody's playing a tone, there's maybe a little ringing in your ears, or there's the sound of atoms moving around in the air that your ears are picking up, right? Like, there's never completely no signal, but no intentional signal. Intentional signal is the left column, no intentional signal is the right column. And then for the rows, did the participant respond yes, or, indicating that I detected a signal, or did they respond no, I didn't detect a signal? And so you see the four possible, outcomes. So when there is a signal present and the participant responds yes, we call that a hit. And if there's a signal present and they respond no, we call that a miss. And then if there is no signal present and they respond yes, we call that a false alarm. And then if there's no signal present and they respond no, we call that a correct rejection. And of course, what we would like is, our respondents, our participants, to have, hits and correct rejections, and we want to minimize false alarms and misses, right? Signal detection theory, being tested by the Gestalt theorists and stuff throughout the 1930s and 40s, had to acknowledge something's going on inside of our learners' heads if they are having, more false alarms, or they're having more misses, depending on their own internal state of motivation, right? And what else is going on inside their head, distraction and other factors. But in the 1950s, they were really talking about, or the 1930s and 40s, they were really talking about motivation as a possible interfering factor. Here we have a picture of, how a person might respond to a particular tone at a particular amplitude. And you see that, they're, oh, I thought I had breakdowns there. You see them at the bottom there where they're not, nobody's saying that they're detecting it. Nobody's saying it. There's a few are making those, false alarms, few false alarms. And then you see that giant jump where most people are now detecting it, correctly hitting on that. And so you kind of see that on most signal detection studies. What we are curious about is those few people down there at the bottom who are, they should be at zero, right? Because the stimulus isn't there. So why are some of them saying they're detecting a stimulus? It may have to do with motivation. So these early researchers were like, I think something's going on inside their heads. We need to talk about something else. We need to stop just talking about stimulus and response. So a huge thorn in behaviorism's side, verbal behavior. I think verbal behavior is, to this day, still a thorn in researchers' side for a lot of reasons, and we'll talk about that as we get to that chapter. But it was a huge problem for behaviorism because, back in the 1950s, Skinner talked about language, verbal behavior being, just like any other learned behavior. And by learned, he meant you got rewarded for correct language use, you got punished for incorrect language use, and that's how you learned the language. He talked about classical conditioning principles where, the person made an association between two stimuli out in the world and they thought, oh, okay, those two go together, and now I've drawn an inference from that. I just showed my cognitive psychology. I didn't mean to say drew an inference. No, now my behavior has changed, is what I meant to say. Operant conditioning, you're being rewarded or you're being punished, and that's how you learn language. And that makes a lot of sense. I mean, let's be honest, we do learn part of language through these principles. There's no question about that, because there are words that let's just think about your own childhood. Think back to your own childhood and words that you said that were either incorrect or people didn't want you saying them. So the two contexts I'm thinking of is like mispronunciations, and people corrected you. My son, when he was little, called chocolate collocolate, and he'd say, can we have collocolate ice cream? And we go, yeah, we'd have chocolate ice cream. I'm trying to teach him it's not collocolate. So you might have something like that where you mispronounce. The other kind of word that you might have gotten a feedback from is if you were using profanity and your parents didn't want you to use it, right? So you're like, a lot of times kids pick that up first because parents say it so emphatically. So the first thing you say is some stuff you're not supposed to say, and so then your parents try and get you not to do that. So you might have gotten direct feedback about those kinds of words. So think about those things for yourself, and you know that there are certain words that you learn to use, or certain structures that in language that you learn to use through that kind of feedback. So we can't ignore these principles. But in 1959, Noam Chomsky pointed out that pure conditioning principles cannot possibly explain all of language acquisition. And what he specifically pointed to are what are called over-regularization errors. Over-regularization is where you treat all words in the language as if they're regular words. So I'll just use English as my example, but this is true in every language. And anybody who speaks another language can think of examples in your own head and go, yep, I know, you're right. Every language has some exceptions to the normal grammatical words. rules, I mean, the normal grammatical rules. So, for example, whoops, yep, nope. In English, if you want to say that something happened in the past, you put an ed ending on it, basically, or a d sound at the end. So you say walk, walked, right? So that's the rule, and it applies to almost all past tense verbs in English. Until you're trying to think of an example of it in front of your class while you're recording, and you're like, oh, think of another verb that you put an ed on the end of it. Like kicked, killed, kissed. Right? You just put a sound on the end of it, and you've got a past tense. That's how it works. Except for, what about the past tense of drink? You didn't drink it, did you? You drank it. So there's some irregular words. One of the things that Chomsky noticed is, and there's lots of different examples of irregular, by the way. There's, the past tense irregulars. There's what we call superlatives, where typically you add an EST sound, but some words are exceptions, and you don't put an EST sound on the end. For example, most. You don't say mostest, but have you ever heard a child say mostest? Plural, usually you just put an S on it or a Z sound on the end of it, and but there are some exceptions. You don't do it for the word deer. There's not, oh look, there's one deer. Now there's four deers. You don't do that. They're all deer for some reason. I don't get it either. So they're just some irregular words, and they work in, past, pluralizing, superlatives. There's certain structures that long story short, there's not everything follows the rule. If you're a native speaker, you sort of naturally figure out the rules through exposure. If you've taken on a language as the second language, you're really acutely aware of all these irregular words. So anybody who is listening to me and knows that, because English is not their first language, and all those examples I gave are good examples of, yeah, that was super frustrating to learn. And native English speakers are like, I don't know, I don't believe it that people say those wrong things. I don't remember saying them. Everybody goes through a period, Chomsky says, all around the world in all languages where they over-regularize. And so they misapply those endings. And we'll talk about this more in the chapter on language. But what he argued is you cannot blame those errors on reinforcement or punishment. You can't. It doesn't make sense that mom and dad are somehow encouraging you, or your friends are somehow encouraging you for saying drinked. Like, there's no way that that's happening. Most of the time when a child says drinked, their parents correct them right away and go, oh, you drank it? Or don't say drinked, it's drank. They try and correct it in some fashion. They role model it. They don't get it. The kid cannot have picked it up from their parents having walked around saying, I drinked it, because parents don't say drinked. So Chomsky's like, that doesn't make sense. They were not reinforced or punished into using these incorrect forms. Instead, what he said is all we can conclude. The only logical thing is that there has to be a universal grammar in place in our heads from birth until we master our first language by the age of like 5. And by master it, I mean get all the structures and the grammar and all that. I'm not saying your vocabulary is complete. I'm just saying you know how to speak in that language now. The only explanation for how you go from baby to speaking in 5 years and figure out all these irregulars and figure all that stuff out so that you're not doing it anymore is that we carry around with us this universal grammar in our heads. And now, we know that it's probably in, Broca's area in the frontal lobe, where children are on the fly applying the grammatical rules. This flies completely in the face of anything behavioristic. Like, the behaviorist can't explain it like that. And Chomsky and Skinner had some famous arguments about this issue. Skinner tried so hard to bend verbal behavior into conditioning explanations, into learning, his radical behavioristic perspective, but ultimately had to concede. Chomsky's explanation is more simple, which is always a hallmark of a good scientific explanation, has fewer mechanisms for causing the outcome, and explains more varieties of things. And so that was like sort of the death knell of behaviorism. Like, Chomsky kind of killed it. And so now here comes cognitive psychology. The first attempt to describe something called cognition was the human information processing paradigm. That's a nice simple term for it, right? In this paradigm, which my slides have decided not to work anymore, the idea is that you have to go through some stages in some fashion to process from stimulus to understanding or interpreting it in your head and then some kind of output. One model in this human information processing paradigm says that the stages of processing happen in a linear fashion. So you have to complete one part of the processing before you can turn your attention to the next part of the processing, and so on like that. The more stages that are involved in processing this piece of information, the more time it will take to process that piece of information, according to this model. So stage one is detecting that the information is even out there. So let's say you're looking out your window and you see a flower garden, right? So you look outside and you're staring at the flowers and you see some motion and you realize, oh, there's a bee. Okay, that's detection. So I accidentally labeled it at the same time. Detection is I saw some motion. Oh, it's a bee is the recognition. Your brain said, oh, it's a bee. And then the response might be, oh, close the window. It doesn't have any screen on it. And I don't want the bee in the house, right? Or I say, oh, look, a bee, or whatever my response is. But according to this model, you have to do those stages one after the next. You can't do them simultaneously. So you detect it, you recognize it, and you respond. Now, it might be a really quick sequence. So see the motion, label it a bee very quickly. Like might seem simultaneous, but according to this model, it has to happen one after the next. The parallel model says all processes begin simultaneously. So you're looking out the window, you're looking at the flowers, you see the motion, you label it a bee, and you start to shut the window. Like all of those things can happen at one time. The finish time on the task will be determined by the slowest processor. In this example, probably shutting the window is going to be the final thing done because it's going to be the thing that probably takes the most time, right? Have to get up, put your hand on the window, put it, so, like there's more involved. So it's probably going to be the last thing that you do, which might cause us to say, oh, look, it's cereal because the last thing that you did was you responded by shutting the window. The parallel processors would say you actually detected all this stuff at the same time, detected, labeled it, and responded to it all sort of simultaneously. Just it's shutting the window took the most time. The cascade model says that all processes are going to begin simultaneously, just like the parallel did, but in this time, they say that the finish time is going to be determined by the last processor. So you start everything at the same time. So let's say you say stage one, ooh, motion. Stage two, it's a bee simultaneously, but maybe it takes a teeny tiny bit longer. Like I'm done realizing it was motion. I'm still saying it's a bee. And then stage three, again, taking the longest time is going to be, shutting the window, last thing that I do. But the finish time is going to be determined by the last processor. So it's even if, let's say, stage one is shutting the window before I recognize that it's a bee, because shutting the window takes the longest amount of time. In the parallel model, the shutting the window is going to be the last thing. But in the cascade model, the last processor is what determines the amount of time. So even if what that last process was quick, let's say stage one was shutting the window and stage three was labeling it a bee. Labeling it a bee is what's going to determine the response time, because that's really what that last processor is the final output, basically. No matter how quick or slow that final output is, it's the last output. So that's when the clock stops running, is when you make that last output. So the cascade model is very similar to the parallel, but it's just a matter of like how long it would actually, when would the timer stop, I guess, is basically, it's hard to describe. But so these three models were in great competition through the like 1960s, trying to figure out which one best describes how we process information. I'll just give you a little window into the conclusion, and we're going to talk about this more in another chapter, but just the conclusion in case you're hanging on this edge of your seat and you want to know. It kind of depends on the stimulus, whether you go serial, parallel, or cascade, right? Like some things you have got to do one after the next, and it's got to be done in a serial fashion. Other kinds of things, you can start them all at one time, but really the one that takes the most cognitive effort is going to determine how long it takes you to process the information, right? So it kind of depends on the input, the stimulus, what you're doing. The B example is a good one of that's something that you could clearly delineate what probably came first, what probably came second, and then what probably took the most time. Other kinds of stimuli are not like that. So we'll talk about that more in another chapter. All right, let's go ahead and take a break here. We'll come back and we will talk about some modern models that have emerged in cognitive psychology.